Let's see. Okay, hi Dartmouth folks. Okay, so I guess I'm going to start. The couple things I didn't say last time. So we had written Einstein's equation down, r mu nu minus 1/2 g mu nu r equals 8 pi g t mu nu. If you take the trace of this, there's an alternate form. I wanted to write out the alternate form. You take the trace of this, the one is to, I get r from the first, taking the trace of the first one, I get minus 2r, trace of g mu nu is 4, so this becomes minus r is 8 pi g, trace t mu mu. And then you can write Einstein's equation in an alternate form. R mu nu is, I get rid of the r piece, replace it by the trace of t, push it to the other side, is 8 pi g t mu nu minus 1/2 g mu nu t mu nu t lambda lambda. Get the trace. Okay, so in what we're about to do in the weak field limit, it's sometimes easier to use one equation and sometimes easier to use the other equation, so we can just go back and forth anytime we want to. 2. The other thing I didn't say is there is a conservation law, which is the covariant derivative of r mu nu minus 1/2 g mu nu r is the covariant derivative of t mu nu. This guy vanished by an identity that I gave you earlier, which went under the name of Bianchi. And this guy vanishes by energy momentum conservation. That's the conservation law. So we'll verify this in the weak field limit in just a minute. Okay, that's two things from the other stuff. Now we start the section that I call weak field and the Feynman rules. So today we basically just explore weak field, and next time we do Feynman rules. That's pretty much how it goes. So we live in a weak field gravity case. The gravitational potential Gm over r. That's if you know your dimensions, that's dimensionless. G goes like 1 over m Planck squared. M is the mass. R by the uncertainty principle goes like 1 over a mass. So this is dimensionless. This guy is about 10 to the minus 9 for us right here in this room. It's about 10 to the minus 6 at the surface of the sun. And as big as it gets in sort of ordinary stuff, 10 to the minus 4 white dwarfs. Okay, of course, if you have a black hole, it gets of order 1 in some field, in some units. Okay, but this lets us imagine that the deviation of the metric field from being essentially flat, we feel almost flat here, is somehow small. So the weak field limit is going to be g mu nu is eta mu nu plus a deviation, and I'm going to try to do this consistently. Let's try it. H mu nu. Okay, so kappa, if you remember, was a parameter where we had kappa squared was 32 pi g Newton. So we haven't shown that yet. We show that probably later today. That's the identification. This part is putting this normalization here is arbitrary, and most relativity books won't do it, but we do it because it makes the propagators normal propagators. So when you do field theory, you tend to do this. Because then when I find the propagators next time, it will have ordinary form. It also makes the field H have the units of mass to the first power, which is the normal scalar field or normal boson field dimensions. Because remember, G is dimensionless. Then if kappa goes like G Newton, which is 1 over the Planck mass, so kappa squared goes like 1 over the Planck mass squared. So kappa goes like 1 over a mass. So H has to go like a mass. Okay. Since we have G mu nu, G nu sigma equals delta sigma, what do I have? Mu. That implies that we have to have G upper. So if I had G upper mu nu, it's eta upper mu nu, which is the same thing as lower mu nu. There's a minus sign here, H mu nu. And then there's a second order term, H mu lambda, H lambda nu. Okay, this guy can be taken as exact, even when we're expanding. The one with the upper indices then has corrections however many orders you expand. So eta plus something, G is equal to eta plus kappa H can be just a definition of H. When H is small, it's useful to expand the upper indices. So the upper index X1 has this longer expansion. Okay, and just for reference, let's just do square root of minus G is then 1 plus a half H lambda lambda minus 1/4 H lambda sigma H sigma lambda plus 1/8 H lambda lambda quantity squared. So I don't think we use that for quite a long time, but since I'm doing it, might as well just do it here. However, more interesting is what the curvatures are. The curvatures R mu nu alpha beta is, in this normalization, I have a kappa floating out in front. If you look it up in a GR book, you probably don't see that, but then it goes like d mu d alpha H nu beta, and it's antisymmetric in alpha beta and mu and nu, and so you can write out all the rest of the terms. I mean, in some sense it has to be this way. Antisymmetric in mu and nu in alpha beta, so it's d mu d beta H nu alpha. It's also then minus d nu d alpha H mu beta, and then the last piece is d nu d beta H mu alpha. I have to R mu nu. Remember, there's a convention on what you contract when you contract it. So let's just write it out in my convention. kappa over 2. I hope this is, sure hope it's my convention. I've taken it from old notes. D mu h lambda nu plus d lambda d nu h mu lambda minus d mu d nu h lambda lambda minus box h mu nu. Okay, this box here is flat box, so it's really box 0, which is eta mu nu d nu. Has no g mu nu's in it because we're working only at this stage. We're working the first order. We're doing an expansion, and R itself is then that's so this guy is symmetric in mu and nu, which you should be able to see. You contract it up with g mu nu, you get 4 terms contract down to 2 terms times with 2 things the same. D lambda d sigma h lambda sigma minus box h lambda lambda, and again that's box 0. All right. So without writing it all over again, we then have r mu nu minus 1/2 eta mu nu now, r, where these guys follow from up there, is, all right, is so it's kappa squared over 4 TB do. And if you'll indulge me, I would like to just do the energy conservation at this stage here. Let's see if we can check energy, so the conservation. We know T mu nu satisfies the conservation law, so that the right-hand side had better do that too. So let's see if I can take d mu. I just have regular derivative at this order on r mu nu minus 1/2 eta mu nu r. Let's just try to write that out. So there's a kappa over 2 floats in front of everything. The first one, I'm taking derivative mu, so it's d lambda box h lambda nu. From this guy here, the derivative there. The next one is d lambda d nu d mu h mu lambda. So there's 2 derivatives, both acting on that. Last one is another box. Next one is another box d nu h lambda lambda, and then this is minus box d nu h d mu h mu nu. Okay, I'm floating my indices up and down. Sorry. And then the next piece here, when I have the factor of r, eta mu nu becomes then the derivative nu, and you get derivative nu d lambda d sigma h lambda sigma minus d nu box h lambda lambda. And so if I've done everything right, these things should all cancel. These 2 guys right here, the first and the last guy cancel, dot, 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 they cancel. Then this guy, oh, I have a minus sign out there. Those 2 guys cancel, and those two guys cancel. I get 0. It's then consistent with conservation of energy and momentum. Okay. That's great. Now let's try to solve it. So here's a wave equation, and this wave equation is basically unsolvable. Okay, and what happened there? There we go. Here's how you would try to solve it. And I'm not going to do all the algebra here. There's some moments where it's just not worth it. But this equation up here, r mu nu minus eta mu nu r, is some differential equation where I've got two derivatives acting on h. Okay, so I would write that out as some operator, some differential operator, mu nu alpha beta h alpha beta. Okay, so this is the derivatives, two derivatives in various combinations. Okay, and that, so I've got a kappa over 2 there. I'm going to make this kappa over 2 t mu nu. Okay, so the way you would try to solve this, the way you would solve it is you would look for a Green's function. So if O mu nu, let me put the alpha beta up there, some Green's function alpha beta gamma delta. So the differential operator on a Green's function of x minus y. If this was something like, well, let's make it 1/2 eta mu gamma eta nu delta plus eta mu delta eta nu gamma times the delta 4 of x minus y. Then you would have a solution h. Let's see, I brought these things down, I guess. Alpha beta of x is the integral d4 y g alpha beta gamma delta kappa over 2 t gamma delta. Okay, if you could find that, then you've solved. That's the solution. Now, here's the trick, is that g alpha beta gamma delta does not exist. You cannot find one. Okay, this guy here basically is just, just to get the indices right. And if anyone's confused about that, I can talk about that. This is some guy I often call I mu nu alpha beta. It basically takes the indices from one side and makes it puts them on the other side. Okay, and so that basically, if I did this differential operator on this thing, it would turn gamma deltas into alpha betas, and I'd have the equation solved. Okay, now the way to show this, which of course I can always leave as an exercise for the student, that's great fun. You write out G as the Fourier transform d for k e to the I k dot x minus y of all sorts of things that you could have. You could have I mu nu alpha beta with some function of k squared, a of k squared. You could have k mu, k nu, k alpha, k beta, or some other function b of k squared. You write out all possible combinations. You act on this thing with this differential operator, which is defined from above, and you find that there's no solution for a, b, c, d, whatever there. Okay. This is like, it's just like if you're trying to solve d mu F mu nu equals J nu, and you're trying to find the Green's function box G mu nu minus D mu D nu. G mu lambda is delta, well, it would be delta 4 of x minus y, eta, what's my indices? D mu, G mu nu lambda, okay? This guy also does not exist. And if you've never seen this before, it is worth it to do this guy. Try to do that one. It's much simpler algebraically than the other one. If it was that simple to do the 4 index one, I would do it here, but I've started off down the page on notes a couple of times on this and haven't come up with a good way to do it in under 10 minutes, so it's not worth it. But the interesting thing is we know the solution to this one. This is a standard problem in E&M. In E&M, what you would do is you would fix the gauge on the A field. That reduces it to a simpler wave equation, and then you can solve that one, get an inverse of that one. So that's what we're going to do here. We're going to, sorry. We're going to do gauge invariance. For this, and then we'll choose a gauge to make this a simpler equation. Okay, good. So here's a small coordinate transformation. We're doing the weak field limit, so we can do where the h is small, so we only have to do small coordinate transformations. So x prime mu is x mu plus some small c mu, which is a function of x. So that's a small coordinate transformation. And I'm going to stick a factor of kappa in here just to match up my other kappas. Okay. If I do this, then dx prime mu is dx mu, but then by the chain rule, it's the derivative of mu. Let's see, I want to do it. Just derivative mu c nu dx nu. So the derivative acts on there. So basically you chain rule it, and there's a kappa floating around there, which I have to stick in. If you go, then you look and see what happens to the metric, you get G prime is eta plus kappa H prime, and H prime mu nu is H mu nu minus the derivative C nu minus the derivative nu C mu. Okay, and it basically cancels off these guys. Those pieces there get canceled off. So this is supposed to be an invariance. Okay, so all the curvatures are invariant under it. Let's just, so curvature is invariant. I have written out on my notes all of them, but let me, for class, just do R itself, because that was the action anyhow. So if the action's invariant, everything else is going to be invariant. So R had two pieces. R has the derivative, where both the derivatives get contracted up to the H indices, and the other one where there's a trace. Okay. So R prime is the original R, and then there's pieces where, so it's minus. There were pieces where I had derivatives contracted up to H, so d mu, d nu, and then it would be contracted up to the derivatives here, d mu c nu plus d derivative nu c mu. Okay, so that's the one where the derivative is contracted directly to H. And then the second one was, had the opposite sign, had a box, and it had H lambda lambda in it. H lambda lambda then gives me 2 d mu, or d lambda c lambda. So basically those. And you see the derivatives here, one of them is contracted to form box, the other one goes contracted to this. So these guys, both cancel off each other, and so R is invariant. Okay, so there's the gauge of all the curvatures are invariant. Okay, then we can use this to pick a gauge. Our favorite gauge is going to be harmonic gauge. Often called the Donder. Okay. It's specified by, if I take d mu h mu nu minus 1/2 d nu h lambda lambda, and set that equal to 0. Okay. Equivalently, sometimes if I define h bar mu nu, this is a useful notation, is h mu nu minus 1/2 eta mu nu h lambda lambda. This is then d mu h bar mu nu equals 0. Okay, you can see it's not hard to see that you can do this. You can't always just make it up an arbitrary thing and just say that you can make that gauge change. But this one is not so bad. Let's imagine I initially did not have it. It's easy to see that you can pick an epsilon that for which it works, and here's how you do it. It's d mu, let's make it h prime mu nu minus 1/2 d nu h lambda lambda prime. So that's the one with the gauge transformation, is d mu h mu nu minus 1/2 d nu h. Okay, but then there's a gauge transformation. I claim it comes out the box c nu. Okay, you have to go through it a little bit up here to see it. The derivatives, oh, I think we've done some of the work. No. how much work is it? The derivative on h mu nu gives me the box h piece, so that's the piece that I'm retaining. The second piece here, the derivative in h lambda lambda gives me the d nu dh, and then that's canceled by the second term here where I take the trace. The derivatives are contracted with the h. So basically, the only piece that you can sort of see it, I don't know how well you can see the algebra as I'm waving my little pencil around, but it's the only piece that survives is the first piece. If I take the derivative and the index, the new index is the one that survives and it's box nu. The other guys, there's always something contracted up in it. They cancel. All right, let's take. I can do algebra. You can take my word on this. Okay. If you do that, this is now a simple wave equation, and so you just pick. If this guy's not zero, you pick box C nu is that guy. We know how to solve that just by a Green's function. That's just your standard Green's function equation. So now I've got a gauge where the transform gauge is zero, so I can always go there. Okay, so small. But then you go back up. You go back up, and you see that this satisfies, makes R very simple. So whenever I have then a derivative that's contracted with a derivative acting on H, where the indices are contracted like that, that turns into an H lambda lambda, and the derivative is sitting outside. And let's go back up here and see what happens on R mu nu. On R mu nu, so this guy's got one contracted, and so that's an H lambda lambda piece. This guy has one contracted. That's an H lambda lambda piece. There's two of them. Here's an H lambda lambda piece. There's one of those. It cancels off those two. I'm left over with box H. So again, with a bunch of algebra, then we have the equations of motion. Then, so the various variations of the equation is then I just get box H mu nu equals minus kappa over 2 T mu nu minus 1/2 eta mu nu T lambda lambda. So that's the one variation where this is R mu nu up to a kappa minus kappa over 2. So there's one version, and the other version is box H bar mu nu. H bar, remember, was, I just defined it, is equal to minus kappa over 2 T mu nu. H bar was defined up here. H minus 1/2 H lambda lambda. Okay, so these are Einstein's equations, and this is morally what we were after all along. We want T mu nu to be the source of the gravitational field. Okay, and there it is. Before I go on, let me just do one note that's going to become useful in a minute or two. Harmonic gauge also simplifies life for the scalar field. If I have, remember, the covariant box, this is no longer box 0. This was 1 over the square root of g. d mu square root of g, derivative was downstairs, g mu nu, d nu, this simplifies because if I take the derivative mu, and I'm just going to act on the square root of g mu nu by itself, this is the derivative mu on, well, it's 1 plus 1/2 h lambda lambda times eta mu nu minus h mu nu, and I need my kappas. Okay, so the first order, those are my two pieces there. The derivative acting on these guys, well, there's a piece that looks like, so it's minus kappa d mu h mu nu acting on that piece there. And then since I pulled a minus kappa out, it's a half d nu acting on h lambda lambda. So the derivatives acting on the g factors here give 0 in this gauge. Okay, so then our covariant box, the derivative basically just passes through the g's, square root of g's cancel. Covariant box is just g mu nu, d mu, d nu in harmonic gauge. Okay. So both the scalar wave equation and the wave equation for gravity simplify. Okay. We can also do gauge invariance for the scalar field. Okay, so here the scalar field is phi prime of x prime is phi of x. And if we're going to check the action, we're going to have d by dx prime mu is dx prime dx. And let's put some indices on this then. So I want mu here, nu. If I look at what this is, then it's eta mu nu minus d mu c nu d by dx nu. And our action, so we have an action, so it's s prime would be d for x prime, square root of minus g prime. There'd be a half g mu nu, d mu phi, d nu phi. I don't need to write out the mass term because that's more or less obviously invariant. I asked you to check this guy as sort of as an exercise. If you didn't, you would just find out that the actually this is one, the dx prime piece transforms like 1 plus d mu epsilon nu, and the square root of g piece is 1 plus a half. If I got my signs right, let me just go back up a second. Just as plus, okay. Plus a half h lambda lambda minus d mu epsilon mu. So these guys cancel from the change of variables there and the change there. That's what you could have shown. And then this piece became 1/2 eta mu nu plus h mu nu plus minus h mu nu plus d mu c nu. C and epsilon are the same thing here. I'm sorry. My notes have c in one place and epsilon in the other place. With my handwriting, c and epsilon basically come out looking the same anyhow. So, and I'm sorry. Let me continue my thought here. C nu epsilon mu. So that's how the g mu upper transformed, and then each of the derivatives went like eta mu nu minus d eta mu lambda d mu c lambda d lambda phi eta nu sigma minus d nu c sigma phi blah blah blah. At the end of the day, these guys here cancel off those guys there, and I come back with just the action S again. Okay, so you can see there's a derivative here that when combined with the eta cancels one of those pieces, and the other piece cancels the other. All right, so let's now look at solutions to this. Here's where we prove it's gravity. Let's take a point mass. So T00 is m delta 3 of x, so it's located at the origin. T mu nu minus 1/2 eta mu nu T lambda lambda is then, well, there's 0, 0, so T lambda lambda, Tij is 0. Tij is 0. We're sitting there at rest. But T lambda lambda is then the same as T00. So you get 1/2 m delta 3 of x. You get a 1 in the first place. For the next terms, the ij terms, just this last piece contributes, so I get a 1, 1, 1. Then, did I have my, let me go back up to the equation here. Okay, so my equation is box h mu nu is this guy with a minus sign there. So I have minus box, but minus box is minus del squared because there's no time dependence. H mu nu is minus a half m delta 3 of x, 1, 1, 1, 1. And I have kappa over 2. All right, let's hope I come out with my right. I should have kappa over 4 there because I had m over 2 here. I think it's going to work. Okay. I'm going to then let kappa h mu nu equal, well, you can see h mu nu has to be the same thing on all the diagonals. So I'm going to call it 2 phi g, 2 phi g, 2 phi g, 2 phi g along the diagonals, zeros on the off diagonal. Good, I think it's going to work. So then I get del squared phi g equals, okay, it's kappa squared over 8, because I've got the 2 there, or h mu nu is 2 over kappa, just put it that way, right? M delta 3 of x the solution to this is then phi g of x is minus g m, no, is minus, let's do it right, minus kappa squared over 32 pi 1 over r minus gm over r. This is where we've chosen kappa squared is 32 pi g. Okay. This is well, no, actually we haven't yet proven that this is right, but it, with this definition here, it's this becomes the gravitational potential with a factor of 2 there. Okay. Now, at long last, I end up proving its gravity by putting a particle in a gravitational field. Okay. Any questions about what I've been doing there? I wrote the equation, picked the gauge, solved it for a point mass. Okay. So now here's a particle in a gravitational field. Okay, so recall that box is just g mu nu d mu d nu at this stage. So we're solving box plus m squared phi equals 0, which is g mu nu d mu d nu plus m squared phi equals 0. Okay, we have to watch out. There's phi and there's phi g, which I just defined. I'm sorry, but those are both conventions. So I'm saying phi g is the gravitational potential. phi is the particle. Okay. G mu nu is then 1 minus 2 phi g. There's a minus 1 plus 2 phi g here, minus 1 plus 2 phi g there, minus 1 plus 2 phi g there. Okay, the only one that's going to play a role is this first one, the G00. Well, let's do that now. Let's take the non-relativistic limit. So I'm going to take phi of x and t and write it as e to the minus I mt phi of x and t. Then my equation here is G00, two time derivatives. So I then get G00, which is sitting right there, 1 minus 2 phi g. Two time derivatives acts, there's two of them can act on the m, one can act on the m and one can act on the psi, or both can act on psi. So I get minus m squared. There's two times ways that you can act, one on each piece. I get minus 2i m d0 acting on psi. And then I get a piece which is d0 squared acting on psi. So let's put a big box and put psi out here. Okay. Then I get minus gij del I del j acting on psi and plus m squared. Okay. At this stage, the non-relativistic limit is gotten by doing the following: is the residual time dependence in the non-relativistic limit is small, so I'm going to drop d0 squared compared to one time derivative. So m times d0 is bigger than two time derivatives. And p squared is small, and the field is small, so I'm just going to take, in this case, this is going to be p squared, and I'm going to just take this to be 1. Okay. But I'm not going to do it up over here because G00 is multiplied by m squared, so I can't take G00 to be 1. Okay. So if I do that, I get, so the G00 has a one piece. The one piece, m squared and m squared cancel each other. So the only piece that survives here is the 2 phi. I get 2 phi g m squared minus 2 I m d0 minus del squared psi of x and t equals 0. I then rearrange this. I divide by 2m I get I d by dt on psi is an minus del squared over 2m. That's the usual p squared over 2m piece. And when I divide by 2m, I'm still left over with an m. I get m phi g psi. So I get the Schrodinger equation with the right gravitational potential. This is the gravitational potential energy. The phi we had solved in this normalization was minus g big M. That's the external field. So I get V gravity is minus g big M little m over r. Okay. And there, finally, we've made contact to the usual gravity by the Schrodinger equation. Okay, any questions about that? Let me see what I want to do. Okay. If there's none, I actually have a mini detour. You know, soon I'm going to do gravitons themselves. Something that I find cute. And this is now, what I did here is I did this non-relativistic reduction, got the Newtonian limit out. We can get the post-Newtonian limit if you work a little harder. I'm not going to do it all post-Newtonian. And you can, instead of the Hamiltonian that, is there a question there? I'm sorry. Was there a question in Dartmouth?
No.
Okay, I thought I heard something. I'll let the heavy lifting being done by somebody else here. The people who did it first is Einstein-Infield-Hoffman. And basically, you write out a Hamiltonian formulation, and I have it copied down here, so I'm just going to uncopy it and paste it up here. There we go. So this is the two-body problem for two particles in a gravitational field. So one could be the sun, one could be the Earth or Mercury or whatever. And so if you solve this, you find the precession of Mercury. There's some parameters A, B, and C. The interesting thing, and the thing I want to talk about, is that these things actually have some ambiguities. The usual coordinates that Einstein-Infield-Hoffman did this in, you would find that this is 1/2, A is 1/2 1 plus 3 m1 plus m2 over m1 m2. B is 1/2 and C is -1/2. These are a particular set of coordinates. Okay, but here's the funny thing. We remember we've decided that we're going to let our coordinates be completely arbitrary, and that's by doing the general coordinate transformation. So I should be able to do a coordinate transformation on this. And so, for example, a particular coordinate transformation, I'll make it small, is that R, so here's a coordinate transformation. R goes to R1 plus alpha G M1 plus M2 over R. Okay. And so under general relativity, I should be able to do that. If I'm just staring at this in any set of coordinates, I don't see that, because if I do this change, I change the numbers. The trick to making this work is that this Hamiltonian is an invariant, or physics is invariant under, so the easy ones are B goes to 1/2 minus alpha, it's actually M1 plus M2 squared over M1, M2. C goes to -1/2 minus alpha. You can see that one. And A goes to 1/2 1 plus 3 plus 2 alpha times this factor M1 plus M2 over M1, M2. So if you make a coordinate change, you get the same Hamiltonian if you change the p squared pieces also. So basically, your definition of p changes because you've changed your definition of coordinates. And the whole Hamiltonian has an invariance. And then what's interesting about it is that if you try solving this, you have to find that whatever you solve, like the precession of Mercury, has to be invariant under these coordinate transformations. So you're shifting these parameters, alpha, B, A, B, and C. You'd normally just solve them in terms of A, B, and C. But whatever formula you come out in terms of A, B, and C has to have this invariance. This is a very tricky invariance. I don't know if you ever wondered about that, but I always wondered about post-Newtonian approximations. What happened to the coordinate transformations of general relativity? And that's where they are. They sit. Yeah. In the expression for A there, you got M1 plus M2 over M1. M1 plus M2 over M. Oh, good point. And both those guys should have been squared. So upstairs, let's see, let's get this right. This square goes on the upstairs piece. Thank you. And the brackets go over there. It is dimensionless. Thank you. Good. You can tell the referees here who dimensional analysis at every formula. Good thing. The other thing that I brought in, this is less consequential, but I know of no good use for this. But there's also quantum corrections to the post-Newtonian potential. Okay, if you do exactly what I did up here, this non-relativistic reduction, so I was doing a non-relativistic reduction, and you do it properly, derivatives, P's and Q's don't commute anymore, okay? And if you carry this out to next order, so this is now post-Newtonian, this is in the limit that m is much, much bigger than m. And the answer is there. This is actually a fermion. And it was done by me and Barry Holstein, 1986, AJP paper. It's just a curiosity, but we did it. So here's what it looks like. You do the Hamiltonian for a fermion in a gravitational field. You get sort of the same sort of things. You get the sort of mass pieces first. There's the gravitational potential that we derived already. There's p squared over 2m's. There's the general relativistic correction. There's this phi g times p squared pieces that sit in the Born-Infeld, the Einstein-Infield-Hoffman parameterization. And now that you get two pieces, there's an h bar typo there. You get two pieces from the fact that p and the derivatives don't commute in the wave equations. And curiosities, there's some spin dependence of a spinning particle in the gravitational field, and a new piece that's, Barry calls it Zitterbewegung. It's the sort of fluctuations in the gravitational field. Anyway, I know of no good use for that, but since we're doing field theory, that's relevant. Okay, I'm actually going to stop there. The next thing I do is I'm going to turn back to gravity, and I'll do T mu nu for gravity, and then quantize the gravitons, showing that they have the right energy momentum and polar